Hello everyone, and welcome back to another Mathematics GIS tutorial video. And in this video, I want to discuss the standard equation of an ellipse. Standard equation of an ellipse. And in specifically, the standard equation of an ellipse centered at the origin, that is longer than it is tall. So the standard equation of an ellipse centered at the origin that is longer than it is tall. So basically what I'm saying when I say that is that the ellipse center is the coordinate 0, 0, and that again the major axis is a horizontal line and the minor axis is a vertical line. That's what this whole thing means. And we'll see that there are different equations if they're not centered at the origin, and there's a different equation if it's taller than it is long. So if it's a vertical ellipse instead of a horizontal ellipse. But this standard equation is x squared over a squared plus y squared over b squared equals 1. And what I want to do in this video is I want to connect these four seemingly random variables to our concrete geometric definitions and the graphical parameters that we defined in the previous video. Specifically, we're going to be using foci, vertex, and covertex. So if these terms seem new to you or you don't understand why I put them where I did, again, they're color-coded. I would strongly encourage you to go back and rewatch the previous video. So what we're going to do is I want to start off with x and y. So x and y are just the x and y coordinate of any point that defines this ellipse. So for example, if I were to put a point here, right, its coordinates would be x and y. So these are just an algebraic expression of any point that lies on this ellipse. Okay, so that's x and y. So x and y are any point that lie on the ellipse. Okay, so that's those. Next, I want to talk about A. So A is a special number that we actually have in our diagram here. So A is explicitly defined as the distance from the origin to the vertex. Okay, so let's use blue here. So A is the distance from the origin to the vertex. And put another way, because we're on the origin, right, A is just the x coordinate of the vertex slash x coordinate of the vertex, right? Because if this distance right here is A, then the vertex would have the coordinates A, 0, right? Because the vertex is lying on the horizontal line, which is the major axis. So that's A. B is another special distance that we have, and B is the distance from the origin B is the distance from the origin to our co-vertex. So let's do this in green. So B is the distance from the origin to the co-vertex. So that's that. And so again, just kind of how we were able to define the vertex as a comma 0, because the vertex lies on the horizontal line, right? The co-vertex would be 0 comma b, right? Because the co-vertices lie on the y-axis or the vertical line. So put another way here, right? This is the y-coordinate. Right, this is the y-coordinate of the co-vertex. Okay. So then finally, one other point that we have here is we have the foci. So the foci, at least in the standard equation as we've written it right now, isn't actually presented, right? We've defined all the parameters here, but typically when you see an ellipse, or if you're not given the standard equation, say you're given some other things, typically you're going to be given the foci. You'll be given the coordinates of the vertex and the coordinates of the foci. So we need to know one other special distance here. And this other special distance is the distance from the origin to the foci, and that distance is called C. Okay, so I'm going to make a note of another thing we need to know called C, and this is the distance from the origin to the foci. Right. And so just like with the vertex, right, foci have to be on the major axis, which for a horizontal ellipse means that they are going to be on the x-axis, which means that the coordinates of the foci are going to be C, comma 0, which means that C is also the x-coordinate of the foci. All right, so we have an A, we have B, and we have C. Now, there is a very special relationship that exists between A, B, and C. And that relationship, let me scroll down just a little bit, give us a little more room. There's a very special relationship that exists between A, B, and C. It comes out of the definition of, it comes out of the way that we actually derive the equation, the standard equation, which is a lot of algebra, and we're not going to go through in this video. But if you actually walk through all of the steps, what you'll see is that there's a very special relationship between A, B, and C. And that relationship is that A squared minus B squared equals C squared. And again, we're not going to define this relationship, or we're not going to derive this relationship. But just keep in mind that A squared minus B squared equals C squared. So if we have the distance from the foci and we have the distance from the vertex, we can calculate B. So if we have A and C, we can calculate B. So if we're given the foci and the vertex, we can get the standard equation. So hopefully this made sense. In the next video, we're going to talk about what happens when we rotate the ellipse. So we have a vertical ellipse instead of a horizontal ellipse. And hopefully it'll make sense why that is the way that it is. But if any of this was confusing, where any of these terms came from, why they're defined the way they are, or this relationship down here, again, we're not deriving it, so just sort of accept that this is the case. If you want to derive it, you certainly can go through the math, but again, it's a lot of algebra. So this relationship right here and these three definitions are going to be very important to being able to sort of keep track of what equation you're supposed to work with. So hopefully this makes sense. If anything doesn't, I encourage you to go back, rewatch the parts you're confused about, and as always, please reach out. Thank you.